So the electrons hit the screen one at a time like particles.
Right.
But when both slits are open, we get an interference pattern, like waves.
Even when we fire them one at a time.
Correct again.
Doesn't that strike you as a little weird? I mean, how can something that hits like a particle produce an interference pattern?
Does each electron go through both slits, like a water wave does?
All good questions.
I got it. If we want to know what the electrons are doing, why don't we just look at them?
Yeah.
Someone already thought of that.
Researchers in Tübingen in Germany placed measuring devices next to the slits. When they fired electrons at the slits, half of them went through the left slit and half went through the right.
See? Told ya. Problem solved.
Not so fast.
When the researchers looked at the screen, something had changed. The interference pattern was gone, replaced by a completely random distribution.
Measuring a system disturbs it, and so even though there's interference there when you're not looking at it, as soon as you look at which slit the electron has come through, it collapses into one of those two possibilities and looks like it's acting like a particle.
Many other experiments have also shown that measuring a quantum object disturbs it. It's as if the quantum world is resisting our attempts to unlock its mysteries.
In classical physics, when you measure something, that object stays the same. We're constantly being measured, and I don't change just because the light is shining on me right now. But in quantum physics, if you shine light on an object, you disturb it inevitably. So in particular, when we try to measure something in quantum physics, then what we're trying to measure will be gone.
Consider, for example, that you're trying to measure the position of a basketball. If you can use your eyes, the basketball's flying across the room, you can see where it is, and you don't disturb it. But now pretend you were blind, and all you could do was throw, say you had a pile of baseballs there. You're throwing the baseballs at the basketball, some of them will hit, they'll come back, they'll tell you where it was, but every time they hit, they kick it a little bit, and that ruins the information. And in quantum mechanics, you don't have the option of doing anything other than disturbing the system when you measure it.
So we can't measure electrons or other quantum objects without disturbing them.
That's right.
You still haven't answered my question. What were the electrons actually doing between the source and the screen?
It depends on your interpretation, so we don't totally know.
The recent quantum theory seems so counterintuitive, is that we have been brought upon classical physics.
Physicists have developed a number of mental pictures of what's happening, but there's no agreement about which one's right.
There's something called the collapse interpretation. The idea is that there's only a wave that passes through the slits, and then the wave, when it arrives at the screen, it collapses, so it's only detected in one of the many possible places it can be detected at the screen.
It seems to behave as a wave in between the source and detector, so it can go around these barriers and go both ways through the slits.
The pilot wave interpretation says that electrons are real particles, like tiny, tiny tennis balls, guided by an unseen wave.
In this case, you can explain why the particle is only detected in one place behind the slits, because there's only one particle.
It's this pilot wave that tells the electron what to do. So the pilot wave mysteriously knows about everything, where everything is in the universe, and it feels whether or not there's a one slit or two slits, or one slit open or the other slit open. And it can somehow tell the electron about this and move it around and get it to go different places.
If wave-guided particles aren't your thing, how about parallel universes? The many worlds interpretation explains the double slit experiment by saying that parallel universes are being created all the time.
So in quantum mechanics, we have superposition of different states, and the many-world interpretation says that all these different superposition of states are equally real.
The world literally splits into many copies, and so we only see one thing happening, but there are people in another parallel world who see another thing happening.
While some researchers attempt to construct mental images of the quantum world, others think this world can't be pictured. The Copenhagen interpretation says that we should focus only on the results of measurements in quantum experiments.
When an experimenter enters a lab and interacts with a quantum mechanical system, the Copenhagen interpretation says don't ignore that interaction. It's a crucial piece of what's happening.
very powerful to restrict yourself to questions about what we can see. It's very powerful to restrict yourself to questions about what we actually do, because that teaches you to think about the experiment in a very honest way, in a way that appeals directly to the experiment itself without invoking extra theoretical ideas.
In the double slit experiment with electrons or with photons or with buckyballs or anything, the question is what happens between the source, the double slit and the screen. John Archibald Wheeler, famous American physicist, said, "This is just a smoky dragon," meaning that we cannot talk about it. We can mathematically describe it, but it is impossible to make a picture.